Another linear system that I would like to introduce is the double mass spring problem. So what I want to imagine is that I have a mass that's attached to the ceiling maybe by a spring. And the spring constant we're going to call K sub 1. And then I'm going to attach a second mass to the first mass, okay, by a different spring with a different spring constant. We'll call that K2. And what I'd like to understand is what is the motion of the two masses. So to look at this problem, we're going to need kind of two sets of coordinates. Okay, so we're going to need the position of the first mass. Okay, so imagine that they're right now in equilibrium. So we will call this the x1 axis, where x1 is equal to 0. That's going to be equilibrium. Okay, and then we're going to have an axis that's describing the motion here of that spring. Let's go ahead and we're actually going to point it down maybe. Okay, so this is the x1 axis, and that's going to describe the motion of this mass away from equilibrium. The equilibrium marked out there where x1 is 0. And then we're going to have a second coordinate, x2, that's going to describe the motion of the mass m2, again away from equilibrium of 0. And again, we're going to point that downward. So we'll call this is just like the x1 axis. This is the x2 axis. Okay, so what we need to do is look at the physical assumptions on this system to come up with a set of differential equations to describe the positions x1 and x2. So I'm going to use, again, Hooke's law. Hooke's law, of course, says the force of the spring is proportional to the displacement in the negative direction, so minus k times x. And then we, of course, want to use Newton's law as well, which says the sum of the forces, the net forces on our object is equal to mass times acceleration. And in this case, that's mass times the second derivative of x. And this will be true for both of the springs. So let's look at the forces that are on each of the two masses. So we would have that mass times acceleration for the first mass is equal to minus k times x1, because it's proportional to the displacement x1. And then we could add some friction, so that would be like minus b times x1 prime to add some friction there. And then we would also have a force of displacement that came from the second mass, okay? And so that would actually be in the opposite direction. That would be plus the second spring constant, and then it would be times the difference in the displacements x2 minus x1. Because really, the x2 axis is going to be relative to that x1 axis there. Now I forgot a k1 here times the x1. We could even attach an external force, okay? In this case, that would be plus h1 of t. Now the second mass is going to be similar, so m2x2 double prime. That's going to be equal to, now we're going to have the force coming from mass 1 onto mass 2, so that would be a minus k2 times the displacement, which is going to be x2 minus x1. Okay, some friction, so minus b times the velocity, x2 prime, and then possibly an external force on that second mass. And so now what you see is we have a system of two second-order differential equations. Now, we know how to deal with a single second-order differential equation, but we have not looked at a system of two second-order differential equations before. So the best way to deal with this kind of system is to rewrite this system as a linear system of first-order equations. So we need to introduce some new variables. We're going to let v1 be the velocity. So we're going to say that v1 is the derivative of x1, and then v2 is the other velocity, that's the derivative of x2. Now, if we do this, then we can rewrite our system. We can think about it as being x1 prime equals v1. And then what is v1 prime? Okay, v1 prime, right, is actually, we can think about it as being x1 double prime. And so if we solve for x1 double prime by dividing by m1, we will get minus k1, and this is going to be everything that gets multiplied by x1. So minus k1 plus k2 over m1 times x1. So that's everything that multiplies by x1. And then minus b1 over m1 times, again, this would be x1 prime, or what we will call v1. And then we can also have a k2 over m1 times x2. And then nothing depends on x2 prime, so we'll finally just have h1 of t over m1. And then x2 prime, we said, was going to be the velocity of the second mass, v2. And so then v2 prime, which we can think of, again, as being x2 double prime, is what you get when you divide by m2 in the x2 double prime equation. So I'm going to get a positive k2 over m2 x1 minus a k2 over m2 x2. I made a small mistake. This is actually, nope, that's not right. That is k2. So we have a k2 over m2 x1 minus a k2 over m2 x2. And then finally a minus b2 over m2 v2. That, of course, comes from the friction term here. Finally, we have the external force, h2 of t, which we can divide by m2. And so this is actually a linear system that has four equations for x1, v1, x2, and v2, which are the four variables. We can write this using matrices. So we can think about this as being x1 prime, v1 prime, x2 prime, v2 prime is equal to, we're going to have a matrix here, times the vector x1, v1, x2, v2. And then plus maybe some external force. Okay, so let's fill in the entries. Okay, so in the first equation, we just have a v1 and nothing else. So that means we need a 0 for the x1s, 1 for v1, and then 0 and 0 for x2 and v2. For the v1 equation, our coefficient of x1 is going to be negative k1 plus k2 over m1. Coefficient of v1 is going to be minus b1 over m1. Coefficient of x2 is going to be k2 over m1. And there is no coefficient of v2 in that equation. Now, in the x2 prime equation, it just depends on v2. So we have zeros for the coefficients of x1, v1, and x2, and then a 1 for the coefficient of v2. And then finally, we need the coefficients for the last equation of x1, which is k2 over m2, of x2, which is minus k2 over m2, and then a v2, which is minus b2 over m2. And then there is no coefficient of v1, so we'll make that 0. Now, the external forces do not appear in the x1 prime and v1 prime equations, but they do, and x2 prime equations, but they do appear in the v1 prime equation as h1 of t over m1, and in the v2 equation as h2 of t over m2. And so here you can see, again, it's a non-homogeneous linear system that's going to describe the position and the velocity of each of these masses. Now, let's move on to one more example. I just want to convert, say, a third order equation to a linear system. Okay, so I'm going to start with this equation. It's t cubed y triple prime of t plus t squared y double prime of t plus t y prime of t plus y of t equals e to the minus t. This doesn't have necessarily a physical representation that we can think of, but it's going to illustrate the technique. Okay, so if we want to convert this into a system, we're going to need to introduce some new variables. Those variables are going to be v, which is the derivative of y, and acceleration we'll call a, which is going to be the second derivative of y. Then we can write, say, y prime is equal to v, y double prime is equal to a, and then, in fact, I'm going to write this across for room. So y double prime is equal to a. And then we're going to solve for what y triple prime is. Okay, so y triple prime is in fact going to be negative 1 over t cubed y. Okay, so I'm imagining I'm going to bring the y over here, and then I'm going to divide by t cubed. Okay, negative 1 over t squared y prime. Okay, so again, I'm going to move this term over here and then divide by t cubed. Okay, a negative 1 over t times a using the same logic, and then a plus 1 over t cubed times e to the minus t. And then what we can do with this equation or these equations is that we can make sure that we rewrite them exclusively in terms of y, v, and a. So we will get y prime is v. Y double prime is actually the same thing as v prime. So v prime is equal to a. And y triple prime is actually a prime, okay, the derivative of acceleration. And so this becomes minus 1 over t cubed y, minus 1 over t squared y prime is v, minus 1 over t times y double prime, which is a. I noticed that I wrote a there, but I meant to write y double prime the first time. And finally plus 1 over t cubed e to the minus t. And in fact, we can even write this as a system. We can think about this as the system y prime, v prime, a prime is equal to a matrix times y, v, a plus some external non-homogeneous part of the equation. Okay, so y prime is equal to v, so it only depends on v, so I get 0, 1, 0 to correspond to the coefficients of y, v, and a. V prime only depends on a, so I would get 0, 0, 1. And then finally, the coefficients from the a prime equation are minus 1 over t cubed, minus 1 over t squared, minus 1 over t. And the external part of the equation, the external force or the non-homogeneous part, only appears in the a equation, and that's a 1 over t cubed e to the minus t. Now, this kind of equation is only going to have a solution if the coefficients of the derivatives in the equation are continuous, those coefficient functions. Okay, so essentially, if the coefficients of y, y prime and y double prime, or in this case, y, v, and a, are continuous, then we will have that there exists a unique solution. So that's why we need t to be bigger than 0 here. Okay, because when t equals 0, then the coefficients of y, v, and a, and the coefficient of e to the minus t, like those are not continuous.